Hi guys, BuildZoid here, and today we're going to be taking a look at the EVGA Z390 FTW motherboard. And before we get into this, I just want to point out that I am sick, so if I sound like I'm sick, that's because I am. And I've seemed to have broken GIMP. Oh, there we go, now it's working again. So then, let's get into this. The motherboard is listed on EVGA's own store as for $230 US, so it's pretty much like lower mid-range for Z390. Same price as sort of the ASRock Z390 Tai Chi, the Gigabyte Z390 Ultra, the Gigabyte Z390 Pro Wi-Fi. That sort of is in that same price range. So yeah, with that out of the way, let's get right into it, starting off with the various overclocking features that the board comes with. And the first one here is, of course, the clear CMOS button, so you do get that. It is on the back of the I/O of the motherboard, so if you have it in a case, you can still get to that button without having to, open up the system, which, in my opinion, like that's a good place to put that button for that exact reason. You also only get a single 8-pin power connector for your CPU power, which, I mean, if you've seen all of my other Z390 motherboard videos, you know that I have absolutely no problem with EVGA doing this. This motherboard's really not intended for any kind of extreme overclocking or anything like that. So the chances that somebody's going to run a setup where the CPU is going to exceed sort of, say, 400 watt CPU power consumption is very, very unlikely. Mostly because once you're pulling about 300 watts through the 8-pin, 9900K is actually very, very hard to cool. And the same is kind of true for like a lot of the other Intel CPUs. Is just like the low core count chips. Like once you get into these high power consumptions, the thermal density is so high that it's really hard to cool the damn things. Though I guess if you did run like a direct die setup, you might be able to hit that 400 watt range without needing, well, like you'd still be looking at like custom water cooling or whatever, but it wouldn't be like, it would be actually achievable, because right now 300 watts, even with a 360 millimeter AIO, not really an option. So yeah, like you're going to be hitting well over 100 degrees Celsius with that kind of power consumption. So I see absolutely no problem with the single 8-pin, because the 8-pin can handle at least 400 watts, if not more, depending on what kind of cabling your power supply uses. So no problem with the single 8-pin there. EVGA is just doing the sort of reasonable thing instead of getting into the contest with all the other board vendors about who has more power connectors. It's just like, though admittedly, like speaking of who has more power connectors, like this is completely unnecessary, and we'll get to that. But anyway, so 8-pin. Next we have power button, reset button, USB connector. USB connector inside the case. I mean, on the motherboard, like inside the case. Like that's where it's going to be when you install it in a case. I think this is meant for the BIOS flashback feature that EVGA now has on their motherboards. And I mean, if you're also, I assume this is going to be implemented as just a regular USB connector. This would be super convenient for storing BIOS profiles also as like an option. And it's kind of neat for test bench uses as well. So yeah, pretty big fan of that as well. Then we, of course, have our postcode, so that's nice. Makes troubleshooting any kind of boot issues much, much easier. And I think we have the standard little LED. So EVGA has this thing, and I assume it's right there, but EVGA does this thing where they typically have like a little white LED for indicating that your 5 volts standby power is turned on, which basically means that your power supply is turned on. On their higher end boards, they have indicator LEDs for literally all of your voltage rails, but even their lower, like even they're not targeted for like not dark class motherboards, right? The dark is like the flagship that has all the troubleshooting features, but even some of their cheaper boards just have a little indicator to tell you that, yeah, the power supply is actually turned on. So that's nice to have. Going along the edge here, we have a speaker. So yeah, the board will beep at you. You can disable it from the BIOS. That's something I think a few people complained about with the dark, where it's just like the dark has this enabled by default. You can go into the BIOS and disable it. So yeah, that's there. That's also kind of like, that's nice when you don't want to pay attention to the system while it's posting, because once it's done posting, it beeps, or if it's not posting, it beeps as well, and you can look over and figure out why it's not posting. So I do actually kind of like that, but a lot of motherboards don't bother to include that these days, and you can disable it. So there's no harm with that. The post code does kind of make it, redundant, but It still has its minor benefits if you have multiple systems and you don't want to pay attention to the one with this motherboard in it. And then finally, we do have this extra 6-pin power connector, which is just completely pointless because that's one 16x slot, that's another 16x slot, and yeah, it's kind of that. I don't know why you need extra 12 volts power for your PCIe slots. Like, the reason why this kind of extra power connector exists on a lot of motherboards, like some motherboards will have a Molex connector. Asus likes to use Molex. I really don't like that, but sometimes, like a lot of the times, it's like a 6-pin, and at least EVGA has enough sense to not put it right there. Like the number of board vendors who put an extra 6-pin like right in the middle of the motherboard, it's just like, who's gonna pull it? Like, it's like the worst possible place to put that power connector. Like, it couldn't be worse. Like, there isn't a more inconvenient location on the entire board that you could have possibly put it in. But anyway, so, you know, sometimes you get Molex, sometimes you get SATA. EVGA likes to go with a 6-pin. I prefer the 6-pin. That's a much more robust connector. And the idea behind these is that basically your 24-pin power connector does not actually have all that much in the way of 12-volt power connections. So it basically just has 2 pins for 12 volts, and that does mean that once you start exceeding sort of 200 watts, 12 volts power draw, you start running the risk of melting your 24-pin, which is not exactly uncommon if you're running like a 4-way GPU or a 3-way GPU setup where, you know, each GPU can happily pull 75 watts from the PCIe slot it's on, and, well, 75 watts plus 75 watts plus 75 watts is about 225. 24 pins pretty not happy at that point. If you have 4 GPUs, that's 300 watts total PCIe power consumption, and at that point, you can just forget about the 24 pin surviving it. So that is like, that's why basically these extra power connectors for PCIe power exist. The thing is, this motherboard only supports 2 GPUs, so yeah, I'm not sure what this is definitely not necessary. It's basically pointless because with 2-way SLI, you won't be able to hit that 200 watt figure where the 24 pin maxes out. So yeah, if it was 3-way or 4-way, then this makes sense. But this is a 2-way two-way Crossfire, 2-way SLI motherboard at most. Which funny thing, EVGA doesn't like advertise the Crossfire capability, like Crossfire support. But luckily, Crossfire just kind of works on anything with PCIe slots. Like Crossfire will work off of chips at PCIe slots if you're desperate enough. It's not great for the performance, but it does work. But yeah, so it does support Crossfire as well, but it only takes 2 high-power GPUs. So, I mean, 2 high-power PCIe devices. So, not exactly all that, like, it's not really all that useful. So, that's kind of that with the overclocking features on the motherboard. It doesn't have any kind of dual BIOS or anything like that. So, it is just single BIOS, which is, I mean, that's kind of standard for a lot of motherboards, which I feel like dual BIOS or socketed BIOS chips should be standard in my opinion. It shouldn't be like, especially for like better motherboards, but I guess I'm alone in that thought process. And Gigabyte's dual BIOS doesn't count because it's stupid. It's like a redundant single BIOS implementation that's a little bit annoying to deal with. It's not what I would consider a good dual BIOS, but anyway, so that's kind of that. Now then, VRM situation. Well, so first of all, I'd like to point out that EVGA likes to advertise this motherboard as having an 11-phase VRM, which doesn't work because there's no 1 voltage regulator with 11 phases anywhere on this motherboard, okay? So we have the V-Core VRM, which is 8 phases, not 11. All right, so that's our V-Core right there. Then we have VCCSA, or at least what I assume is VCCSA, because I'm not sure. VCCSA. So that's your system agent power. That's 1 phase. Then we have what I assume is VCCIO, because the board evidently doesn't have iGPU power, which is fine. Well, it's not fine if you want to use the iGPU for any kind of like acceleration type stuff, right? Because there's like, what is it, Intel QuickSync or something like. There's a lot of like applications that now allow you to use the Intel iGPU for basically GPU accelerating various workloads. This motherboard doesn't support that because there's no power, like the GPU literally doesn't get powered on this motherboard at all. There's just no power going to it. There's no VRM for it. So that's a thing, but you have your VCCSA, VCCSA, V-Core, VCCIO. That's another single phase right there. And then you have VDDR. And so you can probably guess where EVGA is getting that 11 phases figure, right? They're going 8 plus 1 plus 1 plus 1. The problem with this is that's VPP right there. Technically also a phase, so we could also go plus 1. This right here powers the I assume that's PCH power over there, so we can go plus 1 again. So, admit, like, EVGA is not the only board vendor to do this. MSI also does this. So how many do we have? Oh, plus 1. Is there any other buck converters that I'm missing? Like single phase designs somewhere? I don't think so. I think that's all of them at this point. So the problem is basically that this is completely useless as far as information goes. If, say, ASRock was doing this, right, and we just cut off the extra ones I tacked on, like, ASRock likes to run two-phase memory power. So you would go, instead of plus 1, you go plus 2. Right, and it just doesn't tell anybody anything, because it's just like, what phases, where phases. There's 11, yes, there's some 11 phases somewhere on the motherboard. There's not one 11-phase voltage regulator. That is a completely useless piece of information. MSI also does this. MSI also goes and they add up all of the phases on their motherboard, and that includes the fake ones. So when they have a fake 8-phase, MSI does, they go like, okay, this is an 8, and then they go plus 1, plus 1, plus 1, right? When it should be like, which the less terrible version of that would be 4 plus 1, plus 1, plus 1. Still useless, right? But at least at that point, we've eliminated the fake 8-phase out of the equation. But yeah, I'm not a big fan of companies just adding up random voltage regulators and going like that gives them a ton of phases. Like, I get why they do it. Everybody wants a higher number of phases, but like, if Gigabyte did this, right, they'd be advertising their motherboards as being 50. What is it? Like 16 phase? No, it would be way more than that, because they have a 12 phase for vCore, right? Then they have 2 phases for iGPU power on we're let's say Z390 Master. The Ultra has a single phase iGPU, but let's go with the Master. So you have 12 phases vCore, 2 phases iGPU, so that's 14. Then they have 1 phase VCCIO, another phase for VCCSA, and then another phase for VDDR. So at that point, we're at what? We're at 14, we're at like 17 phases total, right? Like, this is stupid. And if ASRock was doing this, then ASRock could go 10 plus 2 plus 1 plus 1 plus 2, because they like to run 2-phase memory power. This is pointless. This is completely and utterly pointless. If you're going to say that your motherboard, like, 11-phase VRM is just straight up wrong. If you say your motherboard has 11 phases on it, well, that's useless information, but at least it's not wrong. So yeah, EVGA just, I get that MSI does this as well, but that doesn't mean, like, it's not fine. Okay, like, honestly, just don't do that. Seriously, it's stupid. It's completely pointless. Because if other board vendors were adding up their phases, you guys would end up so badly. Like, really. Like, Gigabyte, ASRock, and MSI have a very good time of just cramming phases on... Like, they're really good at putting a ton of phases on things. There was, like... Gigabyte had motherboards in the past where if you added up the VDDR, like, the various rails that, like, EVGA added up here, you would end up with over 40 phases. Like, this is just a stupid way of doing things. So... Anyway, let's talk about the actual VRM instead of just about the marketing situation, which I'm obviously not a fan of. So one interesting thing before we get into the vCore VRM is that EVGA has actually 2 like separate input filtering inductors for their VRMs. So basically, like this group of phases up here is like the switching noise from this group of phases up here is kind of isolated from the phases down here, because the switching noise basically goes, and then it gets filtered through the inductor, so you get a little bit less switching noise on here. And over distance, that noise steadily gets flatter and flatter. Just over any kind of like distance, it'll kind of go away, but just straight through the inductor. So a lot of it just gets filtered out right here, and then they have that again up here. Whereas a lot of other motherboards, they'll just kind of have one big 12-volt power plane for all of their phases, and then one inductor for that. So it's like isolating just the 8-pin. Which is, like, ultimately, I don't think that actually makes much of a difference here. But it is just kind of interesting that EVGA does do that. That they do have this you know, the filtering setup for the VRM is split between the phases. So that's kind of interesting. Now then, the actual vCore VRM itself. Well, it looks like it's a 1, 2, 3, 4, 5, 6, 7, 8 phase, and it is an 8 phase. Now, it's not a true 8 phase because, like, technically the controller here could support that. This is, of course, an IR35201, which can support anything from sort of like 8+1 phases down to about 6+2, and anything lower than either of those I mean, not 8+1, idiot. 8+0 to 6+2. So it can go anything in those ranges and anything lower than either of those. So you can run like a 1+2, a 2+2, 3+2, or a 3+0, or whatever, like 5+0, 7+1, you know, a lot of different options in terms of what you can do with this controller right here. Here it is configured as a 4+1 because EVGA wanted to save the cost on not having a extra controller for VCCSA. So they don't have to pay for an extra VCCSA controller, but they do end up with basically 4 phases for vCore instead of, you know, straight 8+0. They could have also probably gone for like a 7+1, which would have been kind of like, at that point they would have a kind of like an efficiency issue with the VRM. Like, it would be kind of hard to get the power. Like, I guess they could have gone with like the NVIDIA way of building phases and just had like this really weird asymmetrical monstrosity. But yeah, what they opted for is pretty standard. So 4+1, this is kind of what you'd get on a lot of Asus motherboards in the past. That then goes into an IR3599. And that then finally, so, you know, so the IR3599 is a doubler. So basically that does the ×2 to the +4 to the 4 part. And then at the end of that, you get a bunch of IR3556 power stages. So that's these chips right here. The 3599s are located on the back of the board. These doublers, I mean, they're as simple a doubler as it gets because they also do quadrupling. So there's some other doublers out there which will do like current balancing and all kinds of fancy extras. The 3599 basically gives you the option to take one PWM signal and split it in half or split it into quarters. Which is pretty, like, that's neat, right? That's a really neat feature, but the downside to that is because it can do the, like, it can quadruple, it doesn't have any kind of features like current balancing or anything like that. So essentially it just splits the PWM signal in half, which means you get sort of less than ideal load sharing between all of the phases. But it still improves your input ripple and your output ripple because it is still a doubler and they just inherently do that. Also, being a doubler, it does put a little bit of delay onto your PWM signal, so that kind of has some negative impact on your transient response, but I think EVGA should do really well in the transient response department just because of the inductors they use. EVGA likes to use one of the lowest inductors out of any motherboard vendor that I'm aware of. Like, these things are 150 nanohenries, which is crazy low. For comparison, Asus on like their Maximus 10 series and on like, if you go basically into the past Asus motherboard models, and even now, they still run a 400 nanohenry inductor, which like essentially when you go higher inductance, you get a benefit in VRM output ripple, but you get and you also get a little bit more efficiency. But you get a big downside basically to it is that you end up with a bunch more energy being stored in the inductor. So when you go from a high current load to a low current load, you have a whole bunch of energy that you need to get rid of, stored up in the inductor. And that's a lot more than if you have a 150 nanohenry inductor. So like when you're talking about really, like when you look at something like the fully integrated voltage regulator from Intel or the integrated voltage regulator from Intel, they're both kind of the same thing. One of them just does more voltages than the other. But both, like, the idea behind the Intel integrated voltage regulator is that it's ridiculously fast. So it runs at several megahertz, like tens of megahertz switching frequency. And so it uses very low inductance, and so it basically doesn't have to worry about transient response because the thing can, like, it has very low inductance, it's right on the CPU, right? It doesn't have a lot of the issues that your external voltage regulator has. So yeah, that's like an example of like transient response optimization to sort of the extreme where you just put the regulator right on the chip, and then you can use really, really low inductance, very high switching frequencies, and and you don't have to worry about having a load line at that point because the regulator can keep up with any kind of current transients just by nature of how it's designed. But with an external one, you need a load line to sort of maintain regulation. But yeah, EVGA is kind of interesting in that they seem to be really fond of 150 nanohenries, whereas say like Asus uses 400, Gigabyte likes to use 310. And MSI tends to, like, sometimes MSI either goes 450 nanohenries, I think it is, or 420. MSI tends to, so that would be Asus, GB. MSI likes to either go for 420s divided by 2, so that's when they run them in parallel, which gives you about 210 nanohenries effective. And then when they don't run them in parallel, they actually run like 220s, if I remember correctly. So yeah, EVGA is really, really low, which should give them, an advantage in transient response. But the trade-off for that is typically that you get more output ripple, though the doublers can can heavily compensate for that downside. So yeah, ultimately, it's just very different approach to VRM design, and you can't really say how this would perform in the real world just looking at the PCB in terms of voltage regulation, but it's just like, yeah, interesting approach. I figured I'd point that out. Now, what we can talk about, but basically just from paper, is efficiency. So, IR3556s, what do you need to know about them? Well, they're a power IR stage. So no, it's POW IR stage. It's an international rectifier power stage. It does 50 amps. Yeah, so it's like the slightly smaller brother of the 3555 that Asus likes to use. So yeah, it's a 50 amp power stage, and there are 8 of them. So the VRM is actually pretty it's a pretty powerful 8-phase. Like, you don't really get, yeah, you could go for 60s. And you can actually get 70s, and then there are also there's I think Texas Instruments has a 75 amp part. So as far as power stages goes, this is, right now, for a long time, your options were basically 60 down, but right now it's 75 down. But still, 50 amps is not a small power stage or anything, so overall VRM efficiency is pretty good, especially at this price point for the motherboard. So yeah, and for the VRM efficiency, VRM operating parameters, we're looking at 400 kilohertz switching frequency, 1.3 volts output, because these have a nice complete data sheet, and 5 volts drive, just because apparently nobody actually runs these on 7 volts, which is really annoying because the data sheet is spec'd in 7 volts, and then there's this lovely part of the data sheet where they show the efficiency decrease by running these chips on 5 volts instead of 7 volts, and it's not it's pretty significant, but apparently there's reliability issues with these chips if you try to run them on 7. So yeah, everybody ends up running them on 5. So then, what kind of VRM efficiency, what kind of heat output does the VRM have at the various current outputs that I normally go for? So starting off at 150 amps, which is 9700Ks, 8086Ks with D-lids, 9900Ks with inadequate cooling. 9900Ks with inadequate cooling will hit a bit above that. Yeah, so, that's kind of normal current loading right there. Pretty common load. So 150 amps, you're going to be looking at about 18 watts of heat, which is not bad. It's not the most efficient, definitely not the most efficient, but it is not a complete disaster. And the VRM should have no problem handling that kind of load. Now, going up to 200 amps, it ends up producing about 25.5 watts of heat. And, at this point, the heat sinks start to actually kind of matter. And I'm not a fan of the shroud EVGA has over the VRM heatsink on this motherboard. The heatsink itself looks like it has a decent amount of surface area, decent amount of mass. Mostly, the main priority with a heatsink is the surface area. Now, admittedly, if you make paper thin fins and make them really, really tall, most the heat won't be able to spread through them very quickly. But yeah, so the heat sinks look decent, but there is that shroud over them, so I'm not sure how effective they'll actually be in the real world. But definitely, the VRM shouldn't have a problem handling this kind of load, because this is definitely not the like efficiency wise, it's not the best. It's also not the worst for like motherboards in this sort of price range. But yeah, it's also not anything incredible, and it is worth noting that since it is just an 8-phase, it is more thermally dense than, say, like a Gigabyte Z390 Master, which actually hits roughly around the same VRM efficiency. But just the amount of space that a VRM takes up will actually significantly change how hot it will operate, just because like if you spread your heat over a larger surface area, it's easier to cool, right? Even if your heat sinks are worse or your heat output is higher. So that is worth noting. But yeah, so 200 amps still shouldn't really be any issue as long as the heat sinks are doing their job properly. Now, 250 amps, at this point, we're looking at sub-ambient cooling for the 9900K. This, to hit 200 amps consistently, and not just for like stress testing, you'd probably be looking at like a D-lid, liquid metal, maybe direct die frame. So, this is not something that's particularly easy to hit, but it should be possible if you have enough cooling, and it doesn't necessarily need to be sub-zero. Now, this is definitely well into the sub-zero range, and at that point, the motherboard starts kind of slipping up, as far as I'm concerned. About 35.5 watts of heat, you're going to need some airflow over the VRM. And that's kind of the end of that. Like, if you stick a fan on it, 35.5 watts of heat isn't actually that hard to cool, but you need airflow. It's not like it'll just work if you don't have any direct airflow. If you have direct airflow, it should be fine. If you don't have direct airflow, it's going to get really hot, really, really fast, maybe even overheat, depending on just how bad your airflow situation at that point is. But then again, this is sub-zero, so that's not really surprising. Now, if you were to totally max this out on like liquid nitrogen, you're probably going to end up around 300 amps output for the VRM maximum. And at that point, you're probably going to be looking at about 52 watts of heat coming out of the VRM. That is actually a bit of an issue, yes. Again, if you have airflow, it should be fine. If you're on liquid nitrogen, then the VRM should be freezing over, and you're not going to be running anything that lasts for you're not going to run a stress test that lasts several hours. So you do have the benefit of the fact that the motherboard will be freezing over, so while you're idling, the VRM will be probably covered in ice. And then once you go under full load, well, it takes time for the VRM to go from 0 degrees Celsius to overheating. So while this is a lot of heat, for extreme overclocking, you don't actually need to sustain that for very, very long. So that's not really it wouldn't necessarily be concerning. But it is worth noting that EVGA this motherboard isn't even designed for extreme overclocking in the first place. So that is just if you're doing this on this motherboard, it's just you chose the wrong motherboard as far as I'm concerned. You should be on a completely different motherboard, because there's a lot of things that this motherboard just doesn't do that you need for extreme overclocking, like the various minor rails, there's basically a bunch of minor rails for Coffee Lake, and we have them since Skylake that basically allow you to really max out on liquid nitrogen. This motherboard doesn't have those at all. So, I mean, they're there, but they're not adjustable. So you're not going to be able to max out on liquid nitrogen with this motherboard anyway, and you shouldn't be doing this in the first place. Okay? You should use a different motherboard for that. Now then, going up, so, at this point, all of these are basically just for fun theoretical figures as far as I'm concerned. 350 amps, 70 watts of heat. Delta fan is probably advisable at this point if you want the VRM to not overheat. 5,000 RPM, 6,000 RPM, something like that. Definitely not a viable option at this point. 400 amps is where the VRM ultimately maxes out, so that's where the, 50 amp power stage... 8-phase VRM, 50 times 8, 400. At that point, these will produce about 92.5 watts of heat, which is hot as hell, right? That is completely uncoolable, but this is just kind of the thing is when you get that 50 amp rating on a power stage, it usually means that power stage sitting on a PCB alone, and then with, a great big blank spot of copper just sort of sitting around it to act as a heatsink. It's not really considering several of the chips sitting next to each other and heating each other by proximity and while running. So Yeah, that's not really surprising. So for normal loading, which is that 150 to 200 amp range, this motherboard should be completely fine. So yeah, I'm actually surprised that EVGA upgraded the VRM, because I was expecting this to be the exact same VRM that they had on the Z370 Micro. But now that they have actually gone up to a slightly more powerful well, not slightly, significantly more powerful power stage, but they did maintain the 8-phase design. And they also dropped the iGPU power. There's no iGPU output, and there is no iGPU power. So that is worth considering. VCCSA, same, IR 3556 power stage, so massive overkill there. This rail doesn't pull that much current, so you don't need to worry about that. Quite frankly, that shouldn't even need the heatsink at all. And the same goes for the VCCIO, except here they're not using power stages. You actually have discrete MOSFETs, so you have the high side and the low side. It's controlled by this chip over here, which is the UP1537. Single phase voltage regulator with, voltage regulator controller and drivers. So it drives the chips itself, and the chips, the MOSFETs itself, not the chips. Well, they are a type of chip, but anyway. The high side MOSFET is a 4C10N from On Semiconductor, so our favorite, low end high side MOSFET. But for this application, it's completely fine. Like, there's no problem with using it. And the low side is a 4C05N, which is actually that's kind of different. A lot of other board vendors will go for like a 4C06. This is slightly better. The 5 is slightly better. So, yeah. No problem with that. Massive overkill for VCCIO. Quite frankly, that doesn't really need a heatsink. That doesn't need to be under the VRM heatsink at all, as far as I'm concerned. So, yeah, but that's that. And then for memory power, I'm not actually sure what it's controlled. Well, it's probably controlled by this chip, which is very likely another UP1537. And the MOSFETs, you have a high side and you have another low side. And I'm not sure which ones they are. I think this is these may well, the high side is definitely another 4C10N. I'm not sure if the low side is a 4C05 or a 4C10N. Could be either, and overall it doesn't even matter because DDR4 doesn't really pull enough power for this to be a concern. So you do get a single phase memory power right here. So yeah, that's the memory VRM over there. And overall, VRM wise, I don't really see any issues with the motherboard. I mean, yeah, the V-Core VRM isn't the most efficient one out there, but it's definitely not the worst one out there either. It's a solid 8-phase. The main concern I have with this motherboard is EVGA's BIOS, quite frankly, and the memory. EVGA has recently put out a bunch of 1 DIMM per channel motherboards, which are really good at memory, which are surprisingly good at memory overclocking. And then there's the Z390 Dark, which is just taking memory overclocking to the next level as far as EVGA's motherboards go. But yeah, as far as their motherboards with 2 DIMMs per channel, I don't know which topology they use, so I don't know if this is T topology or daisy chain, and B, I don't know if these things suck or not, because there's not that much information about memory overclocking on EVGA's 2 DIMMs per channel motherboards. So, yeah, and EVGA kind of has a history of having pretty terrible memory overclocking support until the X299 Dark. Because I quite frankly was expecting the X299 Dark when I got mine. I was expecting it to be absolutely bloody awful. And so I was really, really surprised when it wasn't. And I don't know. It seems that EVGA now knows how to do memory, so maybe this board's fine, but that is something that hopefully somebody tests with this motherboard, just how good it does with memory overclocking, because EVGA does only list the motherboard as supporting 4133, and I don't know if that's because EVGA is being honest about what they can do on it, or if EVGA is being generous like most other board vendors, because a lot of other board vendors, they're gonna put, memory speeds specs on their motherboards where it's just yeah, this memory speed might work if you have a top 1% CPU and this very specific memory kit. And if you have any other memory kit, you're not going to be able to hit that speed. And it's just yeah, okay, so that, I mean, technically, yes, under certain conditions, the motherboard can do this ridiculous memory speed. Realistically speaking, you shouldn't be advertising that, as far as I'm concerned. But they can always say, oh yeah, if you bin 100 CPUs, it's doable. and you use this very specific memory kit. So I'm not sure if EVGA has like, you know, done the same thing for the 4133 speed here, or if it's just like, yeah, you should be able to stick just about anything in it and it'll do 4133, or if it's a case of like, yeah, if you use these very specific 4133 XMP spec kits, it'll do it, and otherwise it won't. So that's one concern. The other concern I have is, well, it's not really a concern, but EVGA's BIOS, as far as like VDroop settings go, is just like load line calibration slash, which EVGA calls VDroop settings go, tends to be kind of terrible. Historically, they've basically had a VDroop on and off option, which if that's your two choices, you go with off, because otherwise you're not going to get any overclocking done. And I know everybody's going to be like, oh, but there's going to be load release, you're going to have horrible transient response, transitions, essentially, when going from full load to idle. You're going to get a big pile of voltage overshoot, and then it's going to potentially ring depending on how the controller can deal with it, how quickly how the controller responds to it. But ultimately, like, your other option is to just have tons and tons of VDroop, and the overshoot doesn't it's not long enough, and it's not generally tall enough to really be a concern most of the time. So, you know, if your choices are basically way too much VDroop and no VDroop and some transient response issues, then you choose no VDroop and transient response issues, because yeah, it's not optimal, but it's better than not being able to overclock properly because your voltage is dropping by 200 or 300 millivolts under load, right? Like, at that point, it's just like, it's useless, because you can set 1.5 volts idle and you get 1.2 at full load, and it's just like, well, you're not going to go anywhere with that kind of VDroop. So yeah, hardware wise, I like it. BIOS wise, I don't know. Like, somebody would have to test the board. Memory support wise, again, no idea. But hardware wise, I don't really see a huge issue with it. Like, it kind of comes down to like what kind of cooling the motherboard has. It's definitely not the most efficient thing out there, but it shouldn't have, like, hardware wise, it shouldn't have issues. But the BIOS, you know, the BIOS plays a huge role, and the memory support, you can't eyeball it at all. I mean, even if you know what kind of topology a board vendor is using, it doesn't really help you because there are like really bad implementations of every topology, and there's also really good ones for every topology as well. So yeah, that's the Z390 FTW. And whoa, this video is long. How did it end up 36 minutes? Seriously? Okay. Well, yeah, that is it for this video. Thanks for watching. Like, share, subscribe. If you have any comments, questions, suggestions, you can leave them down in the comment section below. And what else is there? Right, I have a Patreon and t-shirts, so if you'd like to support the channel, you can find a link to all of that down in the description below. And yeah, that's it for the video. So goodbye. I'm gonna go continue being sick. No, actually no, because I'm uploading this later. Yeah. Anyway, I'll hit the stop button now.